Let's look at notes for 6.1, Euler's method. For differential equations that cannot be solved, the slope field can be a graphical solution to the differential equation. The problem with this approach is that slope field is only really good for getting general trends in solutions and for long-term behaviors of solutions. Now, there are times when we will need to have something more. Maybe we need to determine how a specific solution behaves, including some values that the solution will take. In these cases, we must resort to numerical methods that will allow us to approximate solutions to a differential equation. There are many different methods that can be used to approximate solutions to a differential equation. We have already looked at tangent line approximations, which is closely tied to what we're going to do today, which are not bad approximations near the point of tangency, but the idea can be used repeatedly to get increasingly better approximations. We're going to look at a method that is originally devised by Euler and is called Euler's method. Euler's method basically involves walking along a tightrope from an initial point along its tangent line. Instead of walking along the same line the whole time, we change the tangent line with each step. This involves recalculating the point and the slope after each step. This will produce a much more accurate approximation than simply using the original tangent line. The process is pretty easy and repetitive, and the best way is just to kind of go through an example. But just a couple of things that we're going to do. We're going to break up the idea of finding tangent line into smaller steps, and we're going to adjust. After we find the slope, we're going to go a certain distance, and then we're going to find a slope again, go a certain distance, find a slope again, and that way we can continually update our slope to help us determine finding an approximation or finding an approximated value. Okay, so first we must designate the number of equal steps that we would like to take. Call this number n, and the problem will usually tell you how many steps they want you to use to find the approximation. Next, if x equals a is our initial x value and x equals b is our desired x value, then we can find delta x. Delta x simply b minus a over n. So we've seen this before from previous sections. Recall that the slope is just delta y over delta x, and solving for delta y is simply rearranging this equation, moving delta x to the other side, making delta y equals m times delta x. Okay, so this is going to be the chart that we're going to be filling out, and by filling out this chart, we can just simply follow along the information that we need and fill in the blanks until we get to our updated y value that we need. Okay, so x is the x and y. It's going to be your initial order pair. Your slope is going to be the initial slope formula that you're going to use to determine what direction to move, and then you can be able to find the change in y. And after we find change in y, we're going to adjust that to find our new y value, and so on and so forth. So it's important that if you just memorize this chart, then it makes it a lot easier. We can just fill in the spaces and then stop when we need to. Okay, let's go to the back page. All right, given the differential equation dy over dx equals x minus 2 and the ordered pair y of 0 is equal to 5. So our initial point is given here. All right, now we know that delta x is simply b minus a over n, and says find the approximation for y of 0.8 using Euler's method with two equal steps, sketch your solution. So we're starting with the a value of 0, and we're going until we get to a b value of 0.8. Remember, a and b are simply x values where we start and where we stop. So we start at 0 and we stop at 0.8. So therefore a value is 0, our b value is 0.8, and our n, they tell us that we're going to do two equal steps, so n is equal to 2. So 0.8 minus 0 over 2 is 0.4. So each step will be 0.4 units. All right, so first thing we're going to do is we're going to find the approximation for y of 0.8. So we're just going to, from the previous page, we're just going to copy down that table and we're going to start filling this in. So x and y are simply the ordered pair that they give us, the initial point that they give us, 0, 5, so we're going to fill that in. M is just dy over dx, and dy over dx calls for x minus 2. Now the x value is 0, so 0 minus 2 is simply negative 2. Okay, we're going to adjust to find out how much change there is in the delta y, and we're essentially just taking the m equals delta y over delta x and solving for delta y. So this should be delta y over delta x. And then if we rearrange this, we're going to get delta y is equal to m times delta x. Now m we found from the previous space, which is negative 2. Delta x is 0.4. So negative 2 times 0.4 gives us negative 0.8. Now we're going to take that change in y and we're going to find our new y value. So we're going to step in the direction of how they want us to move. So the new updated y value is simply the y value that we started with plus the change in y. So 5 minus 0.8, right? Y plus delta y will give us 5 minus 0.8 will give us 4.2. Okay, so now we have our new y value. So we're going to go to our next line and we're going to continue filling in the spaces. All right, so we know that x starts at 0. We're going to take 2 equal steps. So the first step we're going to move by 0.4. And then we found our new delta y, or we found our new y value to be 4.2. So now our next point after our updated slope will be 0.4 and 4.2. So now we're going to go through this step again. So m is just delta dy over dx, x minus 2. Our x value is 0.4, so 0.4 minus 2. We go back to our rule for our slope. So 0.4 minus 2 gives us negative 1.6. Now to find delta y is just m times delta x. So our m value, negative 1.6 times delta x, which is 0.4. So negative 1.6 times 0.4 gives us negative 0.64. Okay, so now we're going to adjust our new y value. Our y, 4.2, plus delta y, negative 0.64, will give us 3.56. Okay, all right, so now going to our next row, we have another delta x of 0.4, which will bring us to 0.8. And then at 0.8, our new y value is just 3.56. So this is our y value using Euler's method of approximation. All right, example 2. Oh, and then, right, so therefore y of 0.8 is approximated by the y value of 3.56. Okay, going through another example here, example 2. dy dx is 2x minus y. If y is 3 when x equals 2, use Euler's method with 5 equal steps to approximate y when x is 1.5. So we start off at 1.5 and we're going to continue 5 equal steps to approximate when x is 1.5. So we're starting at 2 and we're ending at 1.5. So our a value is 2, our b value is 1.5. So 2 minus 1.5 will be equal to negative 0.1. Well, actually, rather it should be, our b value is 1.5, so it should be 1.5 minus 2. divided by 5, because 5 equal steps, and that will give us a negative value of 0.1. Okay, so we're going to fill in these steps here. We start off with x and y. So x and y, initially our ordered pair is given by 2, 3. When x is 2, y is 3. M is dy over dx, so we go to our derivative rule. So 2x minus y, so 2 times 2 minus 3. 4 minus 3 is 1. And next, we find our delta y, which is just going to be m times delta x. So 1 times delta x, which is negative 0.1, will give us a value of negative 0.1. And then our y sub nu is just going to be y sub nu is equal to y plus delta y. So our y value is 3. Delta y is negative 0.1, so 3 minus 0.1 gives us 2.9. Okay, we go down to the next line. X is now 1.9 because we are our step value is negative 0.1, so we're going to keep subtracting by 0.1 until we get all the way down to 1.5. And then we just follow through these steps. 2.9, we find our slope given our x and y. We find our delta y, which is going to be m times delta x. And then we update our y value, and then we just keep on going down the line. Okay, so there's quite a few steps here because there's 5 steps, but we're going to keep filling in these values until we reach the same, until we reach the y value that matches with the x value of 1.5. In this case, it will work all the way down to 2.61051. Okay, final example. Assume that f and f prime have the values given in the table. Use Euler's method with 2 steps to approximate the value of 2.6. So we're starting at 3, and our y value is 2. So 3, 2. We're just going to fill in these this table, but we have this information to help us make the process maybe a little bit faster. dy over dx. F prime at 3 is 0.4, so we fill that in. Delta y is just going to be m times delta x. So m is going to be 0.4 times delta x is negative 0.2, so 0.4 times negative 0.2 is negative 0.08. Our y sub nu is just going to be y plus delta y. So our y value is 2, and our delta y, changing y, is negative 0.8, which is 1.92. So we bring that value down to our next line for our y value, and we start again. So at 2.8, the slope is going to be 0.7. 0.7, delta y is m times delta x, so delta x times, m times delta x. 0.7 times negative 0.2 is negative 1.4. Y sub nu is just going to be our y value, 1.92, plus delta y. 1.92 minus 0.14 is 1.78. And then our 1.78 is our y value, which matches, is the match for 2.6, which is where we want to stop. Therefore, f of 2.6 is equal to 1.78.